Today I'm going to talk about quadratic form maximization over convex sets, and this is joint work with Woo-Young Lee and Asaf Naur. Let's begin. Right, so formally I'm interested in approximation algorithms for the following two problems. Okay, so I'm given a matrix A, an n cross n matrix A, and I want to maximize X transpose AX, that is summation Aij Xi Xj, such that X ranges over a convex set C. Okay. I'm interested in both this problem and a closely related variant called bilinear maximization, where you want to maximize X transpose By, where X ranges over a convex set C1 and Y ranges over a convex set C2. So for the purpose of this talk, for simplicity, the convex sets are going to be origin symmetric. That is, whenever X belongs to the set C, negative X also belongs to the set C. Okay, and I assume that the convex set is given by a membership oracle. Okay. And it turns out that bilinear maximization is a special case of quadratic maximization. However, the reason I'm interested in both is because quadratic maximization, it's more general. So for that reason, I'm interested in quadratic. Whereas for bilinear maximization, somehow it has enough structure that it admits constant factor approximation algorithms in a wider range of settings. Also, there is an important interplay between quadratic and bilinear maximization that comes in handy both in algorithms and hardness, and this is the other reason why I'm going to consider both throughout. So I'll start with some preliminaries about norms in this talk. So all norms in this talk are over Euclidean space, Rn, n dimensions, and I'm going to denote them by norm sub x and norm sub y and so on. Okay. There is a well-known equivalence and function analysis between norms and origin symmetric convex bodies. Specifically, given a norm x, the convex body is defined as the unit ball of this norm. That is the set of points that have norm at most one. Okay, and given an origin symmetric convex body B, one can define a norm as the minimum scaling of the body that contains a vector x. Okay, so the norm of x is defined as the minimum scaling of the body that contains the vector x. Okay, so let's see some concrete examples. In the case where the convex set C is the unit ball of L2, this is the well-known maximum eigenvalue. That is, I'm using the Rayleigh quotient definition of the maximum eigenvalue. That is, maximize X transpose AX such that X is in the Euclidean unit ball. Okay, and of course, this is exactly computable. On the other hand, the bilinear version of the problem, maximize X transpose AY, X and Y are in the Euclidean unit ball. This is nothing but the maximum singular value of the matrix. Again, exactly computable. Okay. The only time these two quantities don't coincide is when the maximum eigenvalue is not equal to the maximum magnitude eigenvalue. Okay, yeah. So another familiar example. So if we're in the quadratic case and we consider the L infinity unit ball, that is the plus minus one hypercube, the convex hull of the plus minus one hypercube, and we take our matrix A to be the Laplacian of a graph, then this is exactly the maximum cut of the graph. Okay, and Gomez and Williamson gave a semi-definite programming based constant factor approximation algorithm for this problem. And to do so, they introduced hyperplane rounding in the computer science community, and yeah, it's a seminal paper. Right. Similarly, the bilinear L infinity version with no constraint on the matrix A corresponds to the famous Grothendieck's inequality. Okay, so implicit in an inequality that Grothendieck proved is the fact that a certain natural semi-definite programming relaxation for bilinear maximization is a constant factor approximation to the objective. Okay, the exact value of Grothendieck's constant is still an outstanding open problem, and there have been several works improving this constant and trying to understand its exact value. The most recent being Braverman et al.'s work. Okay. The quadratic version of L infinity is also interesting. This was introduced by Alon et al. In the context of defining the Grothendieck constant of a graph. Okay, and an interesting and subtle separation between the bilinear and quadratic case is evident in the case of L infinity. That is, log n turns out to be the best approximation one can get for quadratic maximization over L infinity. and however, like one of the surprising aspects of Grothendieck's inequality is that you can get a constant factor approximation in the bilinear case. Okay, and this log n is tight. One cannot do better in the quadratic case.
The case of P to Q operator norms, where P is less than Q, corresponds to the case where we study hypercontractive inequalities. If you don't know what this is, don't worry about it. I just wanted to highlight through this problem that there is a connection to small set expansion. This is just to emphasize the connection between quadratic maximization and an important problem in complexity theory, namely the small set expansion hypothesis, which is also related to the unique games conjecture. And the best known approximation in this case is polynomial. This regime is more interesting from the inapproximability standpoint.
So yet another example is a non-LP example, is when you take the Schatten infinity norm. So now I'm thinking of an n square cross n square matrix as my instance, and it maps, it's a linear map from the set of n cross n matrices to the set of n cross n matrices. And the norm that I think of, the convex body is the unit ball of this norm, is Schatten infinity, where Schatten infinity is the maximum singular value of a matrix. It's just another way of saying that. In general, Schatten P norm is defined as apply the LP norm to the singular values of a matrix. Okay? This actually corresponds to another famous inequality known as the non-commutative Grothendieck inequality. This was conjectured by Grothendieck back in 1953, and it took several years for PCA to affirmatively resolve this question, in the sense that he showed implicitly that a certain natural semi-definite programming relaxation again achieves a constant factor approximation to this objective, the bilinear maximization over Schatten infinity. Okay, and now Raghav and Vidic gave an algorithmic rounding algorithm for this, algorithmicizing a different, sharper inequality due to Hagerup. Okay, and they use this to show very nice applications to several areas: quantum XR games, some principal component analysis, etc. Okay. Yet another example of a combinatorial optimization problem that is captured is if we take the norm to be the max of L infinity and L1 divided by K, okay, the quadratic version. This is nothing but the densest subgraph on K vertices, assuming the instance is the adjacency matrix of a graph. Okay. This is another combinatorial optimization problem whose complexity is greatly studied. Again, I can go on. There are several more interesting problems, both from inapproximability and approximability standpoint, that this framework captures.
So my goal is to understand how the approximability of quadratic or bilinear maximization depends on the geometry of the convex sets or norms. And my hope is that this theory can be used for both algorithmic and impossibility results for continuous and combinatorial optimization. I hope I've convinced you that this framework is quite expressive and rich, and so such a pursuit is worthwhile. I'm now ready to state, at least informally, our main results. We don't obtain a characterization, but we do give a generic framework for quadratic maximization with the following features. So firstly, it encompasses the situations where constant factor approximation algorithms were known previously. We also provide a rich family of new examples where constant factor approximation algorithms are possible. And finally, we give a near characterization for special families of norms. So for example, for symmetric norms, that is norms invariant to permutations and sign flips, and also for unitarily invariant matrix norms, we nearly characterize when constant factor approximability is possible. So the rest of this talk is organized as follows. First, I'll discuss prior work. Specifically, I'll start with the case of LP norms, which is already very interesting. And as we'll see later in the talk, forms the template for what we expect the characterization to look like. And then I very briefly discuss prior constant factor approximation algorithms that go beyond LP norms. And finally, I'll discuss our generic framework.
Right. Yeah. So quadratic maximization over LP norms. Right. I'll begin by showing you the approach in the case where the convex set is the hypercube, the convex hull of the hypercube, plus minus one hypercube. Okay, so recall our objective is maximize X transpose AX, that is summation Aij Xi Xj, such that the absolute value of all entries is at most 1. Okay, and now we take a natural vector relaxation of this quantity. It's actually a semi-definite programming relaxation, right? But we replace every vector xi, every scalar xi, by a vector ui. Okay, and so we look at summation aij times ui inner product uj, right? And we replace the absolute value constraint by an L2 norm constraint. Okay, so ui L2 norm is at most 1. If you're wondering why we pick L2 norm out of all other norms, it's because in order for this to be a convex program, our variables are actually the inner products. They are not the vectors ui. So the variables of our convex program are actually the inner products of the vectors. And so we needed some quantity that we can express as an inner product. So just another way of writing this is maximizing, summation aij ui inner product uj, where the ui inner product with itself is at most 1. Okay, I'm going to write it yet another way where it's going to be evident why this is a convex program. Okay, so the above is the same as writing maximize the inner product of A with a matrix bold X, right? Such that bold X is PSD and the diagonal entries of bold X are at most 1. Okay, so this matrix bold X is exactly the matrix of inner products of the vectors U. Okay, so this is going to be our vector relaxation, right? And we're going to show that the vector relaxation's value approximates opt. Okay, so the first inequality is trivial. Okay, so the vector relaxation is always at least opt, because given an optimal solution X, we can define ui to be the elementary vector scaled by xi. Okay, so let's say the elementary vector in the first coordinate. So all the ui's are elementary vector in the first coordinate scaled by xi, and it turns out that this will exactly capture opt. Okay, so the non-trivial inequality is the second inequality, and this is what I'm going to show you now. So opt is at least convex program divided by log n.
To do this, it's helpful to keep in mind the following rounding strategy. So let bold X be the optimal solution to the convex program. Now we sample a multivariate Gaussian vector G with mean 0 and covariance bold X. Such a Gaussian vector, conceivably has good value because X is an optimal solution, but it may not lie inside the hypercube. So we choose the naive strategy of just normalizing G by its maximum magnitude entry. So we return G divided by the infinity norm of G. Okay, now the analysis of this rounding is as follows. So we know that the value of the convex program is A inner product bold X, right? And just because we sampled G from the covariance X, we know that this is equal to the expectation of G inner product AG. Okay, now just by the definition of quadratic maximization, this is at most the optimum value times the infinity squared norm of G. Okay, finally, the infinity squared norm of G in expectation is bounded by log n. This is because if I have n unit variance Gaussians, possibly correlated, just applying union bound implies that their maximum is square root log n with high probability. Okay, we know that each Gaussian has unit variance because of the constraint on bold X, specifically the constraint that the diagonal entries are at most 1. This completes the proof.
So more generally, going to the LP case, opt is given by X transpose AX, where X is in the LP unit ball. And now we follow our nose and we relax it in a similar manner. So now we look at summation Aij ui inner product uj again, replacing scalars by vectors. And now we replace this constraint by the summation of the pth powers of the L2 norms being at most 1. Okay. Another way to write this in a way that makes it more evident when the program is convex and when it isn't, is again A inner product bold face X, such that X is PSD, bold X is PSD, and the summation of the P over 2th powers of the diagonal entries is at most 1. Okay. And now we get the strange phenomenon that this program is convex if and only if P is at least 2. Okay, and it turns out that whenever P is at least 2, we get a constant factor approximation by an analysis that is very analogous to what I showed you before. Okay, so we have convex program is at least opt is at least convex program divided by roughly P. Okay, well, okay, so for P at least 2, we have a constant factor approximation. What about P less than 2, right? So it turns out that the best approximation we know when P is less than 2 is polynomial in N. Okay, and yeah, I'm just summarizing pictorially what I showed you earlier. We get a constant factor approximation when P is at least 2 and strictly less than infinity. And when P is equal to infinity, this is what I just showed you regarding the hypercube, you get a log N approximation. Okay, and indeed, it turns out that you can get some complexity evidence that there is no constant factor approximation algorithm when P is less than 2.
Okay, next I'll survey known results beyond the case of LP norms. Yeah, and constant factor approximation algorithms were obtained in several other norms that aren't LP norms, like the Shatton classes or norms with 2 convexity constant 1. Notably, the result of Nauer and Shetman serves as a big inspiration of this work. In all of these cases, the approach is similar to the LP case. Specifically, one looks at the convex relaxation A inner product bold X such that bold X is PSD, and some function of bold X must belong to the unit ball of the norm capital X. And one identifies for which norms capital X this final constraint is convex. The main difference between these cases and the LP case is that the rounding algorithm or the analysis is sometimes more sophisticated. So I'll next talk about our generic framework for a general norm X. The first issue one encounters is that in previous approaches, it's never clear how to obtain a function f that is computable and moreover satisfies that the constraint f of bold X belonging to ball of X is a convex constraint. In all prior work, this was defined or found in an ad hoc manner. So one of the main ways in which our generic framework differs from prior approaches is that we abandon exact convexity and actually only require approximate convexity from the relaxations we define. Before proceeding, we'll first discuss in detail an important classification tool from Banach space theory known as the type 2 value. So consider the following random walk. You pick a unit vector direction, xi, where unit vector is defined according to the norm capital X. And then you take a step either in the direction xi or the negation of that direction. And you repeat this process for n steps. So the type 2 value of the norm X is defined as the minimum value C, such that after n steps of this process, you are expected to be at a distance of C times square root n from the origin, where the distance again is measured in the capital X norm. Okay, so we'll denote this value by T2 of X, right? And again, it is the smallest value C such that for any sequence of choices of directions, the expected distance from the origin of a random signed combination of these directions is C times square root n. This notion is closely related to a quantitative version of smoothness, to give some intuition. Let's see some examples. So in the LP case, whenever P is at least 2 and less than infinity, we see that the type 2 is a constant. In fact, it's linear in square root P. When P equals infinity, the type 2 is square root log n. And when P is less than 2, the type 2 is polynomial in n. So we see that the squared type 2 constant nicely lines up with the approximability of the LP quadratic maximization landscape. And the same thing happens in the Shatton P case. the approximability and type 2 landscapes line up. Given this, it's natural to conjecture that maybe type 2 characterizes the approximability of quadratic maximization. Okay. Towards this direction, we show that if the type 2 grows polynomially fast for a sequence of norms, then no constant factor approximation algorithm exists, assuming the small set expansion hypothesis, which is a commonly used complexity assumption. Okay. To say maybe one line about the proof, the proof strategy is quite simple. We use structural results from Banach space theory. Specifically, we embed LP norms into the norm capital X in order to reduce from LP quadratic maximization when P is less than 2. Okay. And in fact, if we assume something stronger, we assume the small set expansion hypothesis and the exponential time hypothesis, then we can rule out even very slow growing type 2. So if the type 2 grows even as 2 to the log to the epsilon n, no polynomial time constant factor approximation algorithm exists.
So it turns out that even when the type 2 is bounded by a constant, there are examples where it's information theoretically impossible to approximately solve quadratic maximization. Specifically for the convex hull of the unit sphere spiked in a random direction, it is hard to estimate the L2 radius even with sub-exponentially many membership queries. Okay, and we just exploit the fact that quadratic maximization can easily capture the L2 diameter of a convex body. So it turns out one still has a strong lower bound. So it, similar to the case of convex optimization, where one has to sort of investigate on a case-by-case basis the existence of separation oracles. It seems that we might have to do the same for quadratic maximization, right? Yeah, we still propose a generic framework that can recover what was known before. And now, motivated by the Gaussian rounding from earlier, we give a relaxation that is not convex. Okay, so we just maximize A inner product bold X such that bold X is PSD, and the expected squared norm of a Gaussian sampled from bold X must be at most 1. Okay, this is motivated by Gaussian rounding from earlier. And of course, by the earlier analysis, verbatim, we actually obtained that that nothing has changed. So the value of this relaxation is equal to opt. Right? Of course, note that this is not convex. The connection to type 2 is actually now becomes evident in that this program, while it's not convex, is approximately convex. It's approximately convex within a factor of type 2 of x squared. Okay, so we actually have a certain generic relaxation such that when type 2 is small, this generic relaxation is approximately convex. It turns out that approximate convex optimization cannot be done in general. But we do show that you can just extend the ellipsoid method with the following assumption. Right? So if this set X PST such that Gaussian norm is at most 1 has an alpha approximate separation oracle, then in polytime one can compute an alpha approximation to opt. Okay, what do I mean by an alpha approximate separation oracle? This time, whenever a point is outside an alpha scaling of the body, you have an algorithm to return a hyperplane separating the body from the point. Okay, and by the approximate convexity fact I mentioned earlier, whenever alpha is at least type 2 of x squared, such a hyperplane always exists. Finding such a hyperplane is not clear, right? There's not necessarily an algorithm to find this for a norm x, but such a hyperplane always exists. Such a result is quite straightforward to establish. It's essentially a modification of the ellipsoid method. Okay, so it seems that we have just changed the problem from the design of a convex relaxation to now the design of a separation oracle. But it turns out that we can use classical tools from Banach space theory, like the factorization theory of linear operators and generalized versions of Khinchin inequalities to design such separation oracles. And we use these tools to obtain the following algorithmic results. So firstly, we show that the existence of constant factor approximation algorithms persist under several type 2 preserving operations on convex bodies with bounded type 2, like Minkowski sum, intersection, subspaces, quotients, and complex interpolation. This provides a rich family of new examples for which we obtain constant factor approximation algorithms for quadratic maximization. Okay. Also, assuming the small set expansion hypothesis and the exponential time hypothesis, we show that having bounded type 2 completely characterizes the existence of approximation algorithms for the special families of symmetric norms and unitarily invariant matrix norms. Okay, so while the more general landscape of bounded type 2 is nuanced and a characterization is not clear, in these special cases of symmetric and unitarily invariant norms, type 2 is the characterization. And finally, we obtain versions of the above results for the more complicated bilinear case, where we're able to relax the assumption, the bounded type 2 assumption, to a weaker assumption of having bounded dual cotype 2. This concludes my talk. Thank you.